Hello, I will be presenting our work titled Attainment Regions in Feature Parameter Space for High-Level Debugging in Autonomous Robots. This work is part of the Offshore Robotics for Certifications of Assets Orca Hub project. To deploy robots in everyday tasks, we need them to be able to still perform in every condition or scenario that they face. This idea is related to the robustness of the robot and how well it keeps performing under external perturbations. These perturbations could come from other agents or maybe environmentals. It is not feasible to design a controller that is able to respond to every perturbation when there are complex nonlinear dynamics between the robot and the environment. It is hard to predict such interactions, and on a vast action state space, it is impossible to explicitly model every perturbation and action to be performed by the robot to maintain its working regime. Rather than having a fixed controller, an adaptive controller is able to modify its internal representation to respond to these unseen scenarios. For these motives, we believe that adaptability is a good approach towards robust robots. Our approach is to identify regions in a Euclidean space defined by high-level features of the environment and parameters of the controller, where we know with some degree of certainty that the robot is able to solve the task at hand. The identification of these regions allows us to fine-tune the controller, make robustness analysis, adapt the controller to unseen scenarios, and explain its behavior. We define attainment regions as regions in the feature parameter space where the robot is able to succeed in a task with a defined probability. The work related to robustness in control theory includes the notion of gain and phase region, where a plant remains stable while externally disturbed. Using disk margins, the controllers can be fine-tuned to extend these regions. However, this approach requires an explicit model of the dynamics. Another work is the one related to safety boundaries, where the author used these boundaries for robust control and to estimate safety properties of the controller. One approach is to learn viability kernels at the expenses of sampling directly from the state space. Using signal temporal logic, work from Fan et al. Design partitions of the parameter space of a controller with expertly designed constraints. Also, Dreossi has studied reachability and parameter synthesis to arrive to a user-specified region of interest. In our work, we try to alleviate some of these restrictions and assumptions of these approaches by learning regions in the feature parameter space. We define attainment regions as closed sets in a joint space of features of the environments and parameters of the controller that predicts the performance of a robot in a specific task with a predefined minimum probability of success. Attainment regions allow us to debug the system by finding areas where an expected performance is not met. They allow us to quantify the robustness to external perturbation via high-level features from the state. The controller can automatically adapt its internal representation to solve a task in a specific scenario by finding parameters to enter or remain inside the attainment regions. We can use the attainment regions to explain, based on the features of the environments, why the execution of a task has failed. Attainment regions do not require an explicit model of the dynamics, a large state sampling of the physical system, only on simulation, or expert knowledge about where the limits of the regions are. For any scenario, an internal representation of the controller, we can find two types of solutions for a task that has failed. First, an adaptive solution where the controller makes the smallest modification to its internal parameters to enter the attainment region. And second, a counterfactual solution that specifies the minimum required change in the environment for the robot to solve the task. To formally define our method, Consider a dynamical system where the next state S prime is a function f of the actual action A of the robot and the actual state S. High-level features Z can be extracted from the space. Later on, we will show how to use predefined ones or how to learn them from data using autoencoders. An action A is a function of a controller C with parameters theta that depends on the actual state S. We define a performance function P with features and parameters as arguments that outputs either the success or failure of the task. For simplicity, we write a pair of features and parameters as vector x. The performance of functions outputs a 1 if the result of executing a task is successful, otherwise it's 0. As we are using a simplified representation of the action state space as feature parameter space, we can leverage the power of Gaussian processes to estimate the attainment regions. With a set D of n pairs of the joint space and its performance, we can calculate the mean and variance function of the process. Finally, the attainment regions is a closed set where the prediction of the Gaussian process given the set D is greater than a use-defined performance probability eta sub p. Here are two examples of a slice of multi-dimensional attainment regions calculated from a robotic task simulation. The light blue color is the attainment regions where the prediction of success is above the predefined threshold. The orange area is outside the attainment region, where the prediction is below a threshold. The black line is the boundary of the attainment region. The dots represent sample points in the feature parameter space. With this graphical representation, system designers can gain insight into the controller's performance. They can check for areas where the performance is not the expected one and adjust the parameters of the controller. On a sample-based system like reinforcement learning or any supervised learning system, focus on the limits of the attainment regions can increase the overall performance with less sampling. By calculating the area of the regions, a notion of robustness can be deduced and compared with other controllers, where a larger area represents a more robust controller. The shape of the region can also bring about understanding of the controller, as like in the two images, two different features affect differently the performance of the controller under the same parameters. Also, we can find solutions for unsuccessful trials, finding the closest point from outside the attainment region to its limit. We can define two families of solutions. Adaptive control, where the features are fixed and the solution moves only on the parameters subspace. Here represented by the blue X marks a failed trial. The controller can modify its internal parameters to move the performance prediction inside the attainment region. The second type of solution is a counterfactual one. Here we fix the parameters and search over the feature subspace. You can imagine these solutions as the smallest change in the environment that would allow the task to be solved. For example, move an obstacle that is blocking the way of a robot. These type of solutions are a powerful way of explaining the behavior of a robot, and usually they lie outside of the capabilities of the robot and require an external agent to perform them. We test our method in a robotics task in simulation, and then translate the results to a physical robot. As you see in the images, we use a husky robot where the task is to reach the top of the ramp within a limited time. The ramp varies in steepness and material with different friction coefficients. We take these two characteristics of the environments as features. First, Z1 represents if there is a synthetic ice on the ramp. You can see them as the white rectangle on the images. This material has low friction coefficients. If the ice is not present, then the material is a metallic wholly top side of the ramp. This is a discrete value feature. The second feature is the steepness of the ramp, characterized by the angle of the ramp with respect to the horizontal plane, between 0 and 30 degrees. This is a continuous value. We use a PID controller for commanding the robot, actuating on all the wheels simultaneously. The three gains of the controller keep Kp, Ki, and Kd are the theta parameters. For accurate translation from sim to real, we measured the friction coefficients in the physical system and translated them into the simulator. We collected 400 data points from simulation with various values for the features and parameters, with at least 3 trials per point. We defined the attainment region thresholds eta p as 0.8, and we fit the Gaussian process with the collected data. These images correspond to a slice on the plane of the feature parameter space. The two images show the attainment regions on the proportional gain and the angle of the ramp. The left image is when synthetic ice is present, and the right one without it. When there is no ice present, the attainment region is larger, indicating the dependency of the controller to the presence of this slippery material. Graphic C shows the dependency of the proportional gain and the presence of ice. A value of 0 in the horizontal axis represents the absence of ice, while a value closer to 1 is when ice is present. It can be seen that the controller is able to solve the task when no ice is present for a value of Kp around or below 0.8. In image D, we can see the relationship between the angle of the ramp with respect to the occurrence of the synthetic ice. As the angle increases, the attainment region shows that the probability of success is reduced. Image E and F show the relation of the integral and derivative gains of the angle of the ramp respectively. The vertical limit of the attainment region shows that there is a small to no dependency of these parameters to the angle of the ramp when there is no ice present. In order to transfer the attainment regions from sim to real, we train a beta VAE autoencoder on images from the camera mounted on the simulated and physical robot. We check for the latent variables in the autoencoders that best represents the two original features. In this case, we generate a set of images by varying the latent space. We mark in red the latent variable corresponding to occurrence of ice, and in green the ones depicting the steepness of the ramp as it highs. Note that the reconstruction quality is not the main goal of this autoencoder, but the extraction of the features. Next, we apply a linear mapping of the latent variables to the original ones. The final corrected performance function p hat of x now includes the extraction and mapping of the features from the physical sensors to the original feature parameter space. We tested the two families of solutions. We found a vector x where the control fails. The value of Z1 close to 1 represents the occurrence of the synthetic ice. Z2 shows an angle of around 13 degrees. The last three values are small gains on the PID control. This feature parameter vector is predicted to be outside of the attainment region. For the counterfactual solution or explanation, the optimal features indicate that removing the synthetic ice would yield a successful trial with at least 80% of success. The other counterfactual solution is reducing the angle of the ramp from 13 to 8 degrees. The adaptive solution is an increase by 1 order of magnitude of the proportional controller. On the left, we see the trial with the original parameters that results in a failure. We use attainment regions to find an adaptive solution for this scenario, where the controller adapts its internal representation with the proposed parameters. We can see that the robot is now able to get to the top of the ramp where the controller is disengaged for the robot to return to the safe zone. We have presented attainment regions as closed sets in a feature parameter space and their potential use in debugging, robust control, adaptability, and explainability. In our setup, we show that the regions and its characteristics can be translated to real setting with the use of standard feature extraction and mapping methods. We presented two families of solutions, one being adaptive control and the other counterfactuals. In future work, we are interested in tackling larger controllers, for example deep neural networks, and extract features from more complex external signals.